Good day, Math 31s. This is Mr. Lemko, and today we're talking about Math 30-1, topic 4.1, which is called Angle and Angle Measures. And as it says, quoted by a famous mathematician, trig is not all triangles. And this was first introduced in grade 11 as you talked about that rotational angle. As you rotated around until you got to some terminal arm, and then you talked about angles in standard position versus reference angles and things like that. So to get ourselves started today, we do need our notes for topic 4.1, angle and angle measures. And today we'll talk about a few things like sketching angles in standard position, which is entirely a review, converting between degrees and radians. And radians is something that is quite different that we are going to have to get used to. And we're also going to determine something called coterminal angles. Co meaning at the same time, terminal meaning ending, angles meaning angles, and solving problems of arc length, angles, and the radius of circles. So in topic 4.1, you see we're doing a few different things, but the first thing I guess to get into is a new type of unit. And under the heading of radians, we've got, like meters and feet can both measure length, radians and degrees both measure angles. So I could say 5 centimeters is equivalent to some number of inches, but I can also say that some angle, like 60 degrees, could be compared to something in radians. Now these are not the same thing, 60 degrees and 7 radians, but radians is another way of talking about angles. I mean, you could say that you're on the hills snowboarding or skiing, and it's not quite as cool to say that you did, a 360 than if you were to say you did a 2 pi. That's actually what a converted unit is. 2 pi radians is actually the same thing as 360 degrees. So next time you're snowboarding or skiing and you do a 360 off a jump, you can say you did a 2 pi, and everyone will be equally as impressed with your math skill. Now I did comment though that if no units are written, radians is assumed. So 60 is degrees, and there's a little degrees sign above it there, and 7 doesn't say radians, but it's assumed to be radians even if it doesn't say it. So you have to see the degrees to know that it's degrees. Now we're going to try to convert between the two to start, and it says that one full circle is 2 pi radians, which is supposed to be the same as 360. There's your conversion between radians and degrees. So just on the right side on the chart, we're going to do a bit of a comparison, and you can see there's a pi in there. It's somehow attached to circles. So if I said 360 degrees is 2 pi radians, how could we get from 360 degrees to 180 degrees? And I know what you're thinking. This is a very perfect color of blue, but also you could divide by 2 to get 180, divide by 2 to get pi radians. So 180 is pi. 90 is a pi divided by 2 radians. Keep dividing in half. 45 is a pi over 4 radians, and you're going to actually have these all memorized. Trust me, you will. Now to get from 60, you could take your 180 and divide by 3. And so take your pi and divide by 3. So pi over 3 is the same as 60. And we'll take that one and divide it by 2. And pi over 6 is your radians for 30 degrees. Now, these are all very, very important ones. 30, 60, 45, 90, 180, 360, all ones that you'll actually come across. Now at the very bottom, we are going to examine 2 different increments. So I would like just to take a moment, and this will sort of fill up this circle, talk about a 30-degree angle, and then keep going to 60, and then to 90, and we can keep working our way around, but what I'd like to do is actually count 30s. It's kind of like skip counting, which you start off in grade 2. We're going to do that, but with angles. So this we're going to call is about a 30-degree angle. Add that, you get 60 degrees. Try to be as close to dividing that into thirds as possible. After that, we've got 90 degrees. And you can keep going faster than me if you're able to. 120, 150, 180. What's after 180? 210, 240, 270, 300, and 330 degrees. Now, that wasn't the only thing. We've actually been able to do that for a long time. What I would like us to be able to do is to actually count in radians. So, how much was 30 degrees? Pause for dramatic effect. And you're right, it is pi over 6. So we're going to say this is the same as pi over 6. Now we're going to keep counting pi over 6's, adding fractions as we go. But we're going to reduce the fraction each time. So we have 1 pi over 6. And then we have 2 pi over 6. But notice that I'm not writing 2 pi over 6. I'm writing 1 pi over 3. That's tricky, right? 1 pi over 6, 2 pi over 6, 3 pi over 6. 3 over 6. 3 pi over 6 is a pi over 2. I'd pause, and if you wanted, you could pause the video and kind of count yourself, but I'll keep going otherwise. Pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. Double check you got those right. 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6 is the same as 2 pi, or sort of 0, the kind of our starting point and our ending point for one full rotation. I could technically keep going and say 11 pi over 6, 12 pi over 6, 13 pi over 6, and so on. You're going to be needing to know all of those reduced forms, but you won't have those memorized by the end of today. So we'll do something very, very similar, and we're going to start, though, with a different first step. 45 degrees is a pretty important, let's say, angle when you start talking about triangles and trig. So we've got the same sort of starting point of 0, and then 1 pi over 4. That's our 45 degree angle, and I'll just reference above. Yep. So 1 pi over 4, 2 pi over 4. Oh, I'm already counting in radians. But again, you'll notice the pi over 2 matches that pi over 2 on the left, which makes sense. But 1 pi over 2, 2 pi over 2, 3 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, which we know is 3 pi over 2, 7 pi over 4, and of course 8 pi over 4, which is 2 pi. Now, I'll write in the degrees just because I forgot to, but we have 45 degrees, 90 degrees, 135 degrees, 180 degrees, 225 degrees, and 315 degrees. Now you'll notice that there are a lot of patterns here, like this is a 45, 35, 25, 15, and all those seem to be a decreasing kind of number ending in a 45. There's also, again, tons of patterns, but this is just the first step of getting more familiar with angles in radians and degrees. We'll flip it on over, and at the top of the next page, a quick convert. Now, there's a number of different ways to convert, and what I found the easiest way to be, so that people don't make a mistake, is start with a fact. So what we're going to do is convert the following degrees to radians, and we're going to try to use exact and rounded answers to the nearest hundredth when rounding. So it's helpful to start with a fact, and I'm just going to pick on the 180 is pi. It's a pretty easy one to work with. And so this converts centimeters to inches, kilometers to miles, grams to pounds, radians to degrees. Start with the fact. Okay. Our fact is that 180 degrees is pi radians. If you start with the fact, then you can write a line on top of each, and put the units that you know, 45, above the units in your fact. So 45 degrees above 180 degrees, unknown radians above radians. Cross multiply to get the x by itself, and this is a simple slide of that pi up there, and we've got 45 pi over 180 equals x. There's your answer. Now, it is helpful to reduce this, and at this point people would grab their calculators, and I will show what that looks like. There is a way to turn an answer into a reduced fraction, and a lot of people think they will get this by saying 45 pi divided by 180 and hitting enter, and then saying math, answer back into a fraction, and thinking you're a little bit genius, you hit enter, and it doesn't turn it back into a fraction. Well, if you look up at the pi number on the wall, it does say that pi kind of goes on for a while. It's in fact irrational. So it can't turn an irrational number into a fraction. So what you can do is forget about the pi for a moment and just type in the fraction without it, 45 over 180. Enter, math answer back into a fraction, and you get 1 over 4. Put the pi back in, and there's your reduced fraction. So a final answer is saying not 45 over 180, but 1 over 4. And I'll put that 1 pi over 4 back in, or a pi over 4. We actually knew that 45 degrees was pi over 4 from the previous page, but this sort of confirms easy, hard, maybe harder level question. Similarly with 240, you could give this one a try. If you wanted to pause the video and give it a try, you can, and then check. I will go through the answer now. A 180 is a pi radian. A line on top of each. The 240 goes on the degree side, unknown x over the radian side, and if you can move that pi up there to cross multiply, we've got a 240 pi over 180. And if you reduce the 240 over 180, and again, a lot of people will simply go to their calculator and say 240 over 180, enter, math, answer into a fraction, and it does tell us nicely 4 over 3. Put the pi back in, and we've got 4 pi over 3 radians, which you can confirm on your 8 pi over 6 rotation. Now this works just the same for example 2, but I did say that we were going to solve as exact and as decimal answers. So just to confirm, there is an actual decimal answer for numbers like pi over 4. So if you type into your calculator pi divided by 4 and hit enter, it actually says 0.785, and to the nearest hundredth we'll call that a 0.79. 0.79 radians. And that's kind of weird, but 45 degrees is like 0.8 of a radian. Makes you wonder what a radian actually sort of is. We'll try to visualize that in just a moment. But example 2 works the same, but we're going to convert in the other direction. So convert the following radians to degrees. So start with the fact. 180 is pi. We can write the units we know, 5 pi over 6 on the radian side, unknown degrees on the degree side, and cross multiply that 180 up there. So we have a 5 pi over 6 that is hanging out next to 180 degrees now, all divided by pi. And the radians will cancel, but essentially this is what we have to reduce. Now some people will say, oh, just type it all into the calculator, and you could. Some other people might say, well, the pi's should cancel. There's one on the top and there's one on the bottom. The 180 and the 6, there's a top and a bottom. 180 divided by 6 is a 30. And 5 times 30 is 150 degrees, which, again, you can confirm very quickly by typing in 5 pi over 6 times 180 divided by pi, and 150 will come out. A very nice 150. So if I were to ask how much is 1 radian, I knew it was radian because it didn't say degrees. I could do the same thing and type in 180 degrees is pi. Write a 1 above the pi radians, unknown degrees above the degrees, and cross multiply. We end up with 180 divided by pi. So how many degrees is 1 radian? Well, if we type into our calculator 180 divided by pi, we've got like 57.29-ish. I'll just call it 57 for the moment. And we've got 57 degrees. So if you were to visualize 57 degrees, there's 45, a little bit more is right there. That amount is about 1 radian. It's a really weird measure, and it's not a very nice one because it is irrational, but that's how much about 1 radian is, close to 57 degrees. Now, a couple other things that are extending out of grade 11 is angles in standard position. Now, angles in standard position is talking about this rotational trig. So what we're doing in angles in standard position is talking about this terminal arm that rotates around. So we have this initial arm that starts right here, initial arm. And what happens is this initial arm rotates around counterclockwise until it gets to some place where it stops or terminates. And I just picked a random location, but this is called the terminal arm. So there's an initial arm and a terminal arm. And what is created as you rotate the entire way is an angle. This angle I will call the theta, but this is an angle in standard position. Angle in standard position. What is created from this angle in standard position, though, is a reference angle. Now, this is created by the terminal arm and the closest x-axes. So right here, there's another theta, another angle. Maybe I'll call this theta 1 and theta 2. Theta 2 is the reference angle. And there was a lot of trig that you did in grade 11 that required you to know the difference between both of those, but there will be a refresher of that. For example, though, if I were to say theta 1 is 150 degrees, and I'll write over top of it. If that is 150 degrees, what would your reference angle be? Reference angle in this case, you could take a 180, subtract the 150, and you would end up with 130 degrees. There's always a little bit of troubleshooting or problem solving between the two. So let's just try on the next page. In example 3, a little bit of a challenge. Can you draw the terminal arm and then convert your answer from the given units to determine the reference angle? So just because it's complex enough this way, let's just see if we can get the reference angle from the angle in standard position. So first we have 150 degrees. So as we rotate around from 0, we have 150 degrees. I know that it's a little bit shy of the 180, but a little bit more than the 90. So if I write 150 degrees in there, I can then ask the question, what is the distance to the closest x-axis? I'll call that theta. And what kind of calculation could be used to calculate that theta? A few people are thinking about it. You're right. It is 180 degrees. Take away a 150, and you'd end up with a 30-degree reference angle. Well, let's try this in 5 pi over 6. A bit trickier, but you might again think back to counting pi over 6s. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. That is so tricky because that's actually the same place. 5 pi over 6. So what are we doing to calculate this angle in standard position? Well, we might say, what is 180 degrees minus 5 pi over 6? Note, though, that instead of writing 180, I wrote pi. Tricky, right? To subtract fractions, we do need a common denominator, and so I'll put a 6 over 6 to say now we have a common denominator, and subtract 6 pi over 6 minus 6 pi minus 5 pi is 1 pi over 6. There's your reference angle for 5 pi over 6 in standard position. Negative 60. Now for the first time we're seeing negative angles, and your teacher may have talked about it a little bit last year, but negative angles simply mean we're traveling clockwise in the opposite direction. So as we were to travel around in the opposite direction, which we'll call negative 60. Now this is actually interesting because in standard position, traveling all the way around, this is actually 300 degrees. So this negative 60 is not in standard position, but 300 would be. Regardless, what is the angle between the terminal arm and the closest x-axis? I'll do this in green. It is right there, no calculation. It is 60 degrees. And the last one, 2 pi over 3. So I'm actually going to count pi over 3's, which are 60 degrees. I know that's tricky, but we're going to try it. That's where 1 pi over 3 is, 60 degrees. Add another 60 degrees about there. So 1 pi over 3, 2 pi over 3 is right about there. And similarly, you can say I need this little angle between my terminal arm and the closest x-axis. That is 1 pi minus 2 pi over 3. And so make a common denominator. And we'll call this pi over 3 radians. Some people might actually start by turning this right into degrees and then saying, I'm just going to work in degrees and then convert it back at the end. And that logic will work, but it is more time consuming. All right, so this brings me to one more comment. Just like in example C, I talked about this negative 60 not being in standard position. There is multiple ways to get to the same place. We call these coterminal angles. Now, coterminal angles have the same location of a terminal arm. A coterminal angle may not be the same value. So I couldn't just say 90 degrees is coterminal with pi over 2. So what we're sort of referring to this idea that as we rotate around, and picture someone dancing, and every time they spin, they're spotting, right? So they're noticing perhaps every time they're facing forward, they're looking in the same direction. When you're spotting, you are looking in the same direction, or you're ending in the same spot. So what we're trying to say is there another angle that defines this location? It's helpful to do a little picture, especially for those that are very visual, and ask, well, where is this terminal arm? Can we get there a different way? So for this first one, we've got a negative 3 pi over 2. And if you're thinking very, very carefully, you might be going back to these rotations and saying, well, where was 3 pi over 2? Ah, that was 270 degrees. You can definitely reference this the entire time. So negative 3 pi over 2 is negative 270 degrees, which takes us right up to the top. So I'm not going to say negative 270 degrees because that's just converting units. But you're already thinking, well, couldn't we have gone in the positive direction and just said, 90 degrees? Yeah, we could have said 1 pi over 2 or 90 degrees. That is coterminal. That is a terminal arm in the same spot. One going left, one going right. Clockwise, counterclockwise. 5 pi. Now, all of a sudden we're talking about doing multiple rotations. This is when Mr. Lumko is on the on his skis or snowboard, and he does more than a full 360. He's doing 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and then he breaks his leg. But we do have this terminal arm that ended right there. Well, maybe we just take off a 2 pi or take off another 2 pi and say minus a 2 pi, minus a 2 pi, take off a couple circles, and we're left with pi. And that is the same thing as we rotate from 0 up until where that terminal arm is. 40 degrees. And maybe we can get